back again. So, I am Jonathan Worthington. I'm a compiler hacker. I write compilers. I'm one of the people who's working on this rather long project called Perl 6, which is taking just a while. I'm one of the core developers of the Rakudo compiler. But I'm also, these days, working on something we're calling a compiler toolkit. That's kind of what I'm going to talk about today. My work focuses on object models, type systems, multiple dispatch, and a bunch of other really easy stuff. I love to travel, especially to open source events. This is places that I've been. Many of them were for Perl conferences. The craziest place I went for a Perl conference so far was Vladivostok. And I like to drink beer. Now, beer drinking normally ends well. But about 3 years ago, I drank some beer and said something that made a lot of work for me. I was at OSCON in a room, and it was a party. And amongst the people there was Patrick Michaud, who's the lead Rakudo developer. And in front of him, and to make it worse, Larry Wall, I said, "Oh, junctions in Perl 6 seem really interesting. I'd like to implement them." What I didn't know is that to implement junctions, you have to implement multiple dispatch. To implement multiple dispatch, you have to implement the type system. And to implement the type system, you have to implement the object model. 3 years later, I'm still working on this stuff. So, Perl 6. It's a language that has quite a lot of needs. It's a language that's trying to be maybe almost a 100-year language. And that doesn't mean that we're going to spend 100 years developing it. That's how long it's supposed to actually be useful for. So if you're going to do that, then you have to be able to adapt. And one of the things we therefore need to build for Perl 6 is this idea of immutable grammar. The idea that the language's syntax can cleanly change over time, but so we can always know what language we're in. So to do that, we figured that we'd have to actually make the Perl 6 grammar be in Perl 6, and that meant we needed a grammar engine. Now, the object model is also meant to be pluggable. If we look at the history of object orientation, it's changed quite a lot over time. Today, inheritance is just an everyday part of our object-oriented life in many languages. But I think really that inheritance is just one way to gain certain desirable things like polymorphism and code reuse. And these days we have other mechanisms that are emerging. So we want to be able to sort of change with that as well. So we need to have some meta-object programming support. And Perl 6, like Perl 5, kind of wants to be a run-anywhere language, but running anywhere today is partly about running on different VMs, running on the JVM, running on this common language runtime. So we have to build all this stuff. And what we actually have had to build along the way so far is almost all of the things that you need to write a compiler. And thankfully, from the very start of working on this, Patrick Michaud said, well, let's keep those parts factored out. So what we now actually have is a growing and very actively developed toolkit that you can use to build compilers, whether you are interested in Perl 6 or not. And that's kind of the sort of thing I want to talk about today. Compilers, in a way, are probably about the simplest sort of program you can imagine writing. They take some textual input, and that's in some kind of source language, and they put out some other input in some other probably lower level language. It's basically input, processing, output. So it's only the stuff that's in the processing that's sort of tricky. Now, one of the things that compilers tend to do is try and stop working with the text as soon as possible. Because working with text is slow, it's kind of difficult, and if you've tried to work with any complex structured document and tried to just do it with, say, regexes or so forth, you normally find that really you have to make some kind of object model first. So one of the first things a compiler will do when it gets some program in is it will parse it. It does parsing, and it actually makes a tree representation of the program. We then probably have a bunch of other trees, and only at the very end do we go back to having some list of sequential instructions that we're going to execute. So if I just take an example here of an expression that calculates how much it costs down at the bar, then we have the number of beers times the cost per beer plus the service fee. Now, the important thing that we need to capture in this is that the multiplication is higher precedence than the addition. So when we have a tree, this is really obvious. After we get this tree, it's really obvious that when we compile this code, the multiplication should be done first and then added to this. This is just one sort of tree that we build when we're compiling. So what we call this tree, like the one I just showed you, the parse tree. This is a tree which is just like the language you write the code in, but sort of in a tree form instead. But when we then want to do anything with it, we're more interested not in the exact words and spellings that are used, but we're interested more in the meaning. We're interested in capturing the semantics. We tend to call a tree that does this an abstract syntax tree. Finally, after that, we want to go and do something like generate code for some virtual machine. So then we use what we call the backend tree. It's a representation that's close to the language we're going to generate. Now, you might think that, okay, now I understand everything, and we go from the parse tree, and then we make an abstract syntax tree, and then we make the backend tree, and then we generate code, and then we're done. Traditionally, this is kind of right, but dynamic languages aren't really like this. If you've programmed in Perl, you've probably come across the idea of the begin block. A begin block is kind of weird because as soon as we finish parsing this block of code, we actually run it before we even continue parsing the rest of the program. So we actually don't really have a compile time that ends and then runtime starts. We generally have a compile time which maybe does some runtime, and a runtime that may be called eval and wants to compile some code at runtime. So one of the sort of tricky things to deal with is that we don't just have this very simple view of the world. We actually have to worry about being able to do bits of runtime as we compile. So when we were working on this, and this started before I got involved, they created the thing called the Parrot Compiler Toolkit. And I put Parrot in brackets now because this is actually something that we're taking beyond that. Parrot is a virtual machine that was aimed at running a bunch of dynamic languages. And we sort of had an intersection here of needs. So on the one hand, we needed some good tools for Perl 6 to be able to write the compiler, but the Parrot folks wanted a nice toolkit for writing compilers. So part of this toolkit is a grammar engine. This is used to actually parse code and make a parse tree. We then have a standardized set of abstract syntax tree nodes, which we call past. What we then realized is, well, once you've made this, then we can turn these into code for a particular virtual machine, and we don't have to make people write the code generation themselves anymore. We can do that bit for them. And then we have a bunch of sort of compiler infrastructure which does all of the sort of boring common things that you would have to do. Things like doing the command line argument processing, managing the overall process of the compilation, maybe giving you some kind of read eval print loop. To actually be able to do this, we kind of wanted a language that we sort of recommended as the language to write the compilers in. And what was created was called Not Quite Perl, or Not Quite Perl 6. This is a really small subset of the Perl 6 language, and it's ideal for doing things like mapping a parse tree into an abstract syntax tree. What's really cool about this today is the compiler for NQP is written in NQP. So that means that the compiler compiles itself, and then we distribute the compiled version, and if we want to change it, we just have to recompile it using itself, which means that if you get a bug in there, then it takes you a few times around the bootstrapping cycle to sort of get rid of it, so I try not to make too many bugs. So what do we do if we were interested in making a language of our own? Well, first of all, we'd have to define what the syntax was going to look like. So we'd write a grammar. Then we'd have to say what the syntax means. Well, that really is just turning the grammar tree, the parse tree, into an abstract syntax tree. After that, all we have to do is write some built-in types or functions, and then maybe we have to write what we call meta objects to implement some object-oriented functionality. So I figured the best way to actually see how this works was that we'd write a programming language today. So we're going to make a language called TinyLang, which is tiny. Here is the program that I want us to be able to run today. So you can see it has variables, which are declared with the var keyword. So there we're just doing an assignment. We then have a class, so we have a dog. This is going to be a class. We'll say it has a method. So, this reads quite nicely. So a dog can bark, and then we just call writeLine and sort of print some output. And then we have a new keyword for making an instance of the object, and we can do method calls. So that's a pretty simple little language, but if we look at what's in there, it's, we have to implement the strings, we have to implement the built-ins, we're going to have to do some operators to do variables and binding, and then we'll have to do the object system. So let's get started. One of the things that we provide straight out the box is a set of base classes that you can inherit from and implement the three main parts of your compiler that you have to write. These are in a library called HLL, which means high-level language. And what we'll do, we'll create three classes. Our first class is going to be for our grammar. The next one will be for our actions. And the third one will be for our compiler. So at this point, we've just declared three classes, which we're going to fill out as we get going. Then we just need to have some sort of configuration. We need to set things up a little bit, and we need to have an entry point for our compiler. Well, what we'll do for this is we'll just write a submain. This is just the main entry point of the program. We'll create an instance of the compiler object. We'll say what the language name is. We'll tell it what grammar and actions to use. And then we'll just say, oh, give me a command line. And actually, as soon as I do that, I actually get something I can run. So if I just do this, okay, so you see already, just by actually doing that bit of code, we already have a prompt. So we can, in theory, type in some code, but it's actually going to say, oh, I don't know how to parse anything yet. So let's do that. When we want to parse a program, generally we think about it starting from the sort of top level and then breaking it down into smaller and smaller pieces. The first rule that we always write is called top. Now, in this case, I'm just going to say that our program is going to be terms separated by semicolons. Well, this is how we write this in the grammar language. We write rule, we give it a name, and then inside the curly brackets, we just say what that rule means. When we have something in the angle brackets, it's a bit like doing a subroutine call. It's like doing a call to a different rule. And then the star star semicolon means match many terms separated by semicolons. When we are looking at our language after that, we then say, well, there's things that we have many of. We have many infix operators. We have many terms. We have many literal values, things like strings or numbers or integers. And we actually have a way in a Perl 6 grammar to make these very explicit. We do this with what we call proto-regexes. So what we do is we introduce a category using this proto. So we say we have a proto-token term, and then here we start defining the different sorts of terms we have. So we say, well, one thing that we could have is we could have a call. And a call is an identifier, which is the name of the built-in function that we want to call. It's an opening bracket. You can see I've put that in quotes, so we'll match it just as it is. We want to have an argument list, which is the arguments that we'll call with, and we want to have just a closing bracket for that. We then say, well, we have values, and all we'll do is just delegate to some value rule, which we'll implement in a minute. An argument list then is just terms separated by commas. So you can sort of see the way that we're breaking our sort of program structure down. We start at the top, which matches some terms, and terms might be a call, or they might be just a value. And the value, for now, we'll just say is a string. And don't worry too much about what this quote expa thing is. It's actually just a quote parser, which matches sort of things between double quotes or various different quoting constructs. So it just saves us actually writing that, and we inherited it from HLL grammar. So at this point, we actually would have a compiler that can't generate any code, but it could at least pass a program. So if I was to pass in, say, WriteLine, and just look at this target pass output, I would actually be able to see that it found a term, and it found a value, and it found a quote expression. So if we think about what we have so far, we take our source code, and we start going down and building this tree which represents our program. Now what we need to do as we go back up is start building something which says what our program means. So in a sense, we build what we call the abstract syntax tree, the meaning of the program up, once we identify each of the small parts. So let's start at the bottom. The first thing that we're going to have is just a value. And what we actually do in our actions class is we write a method with the same name as the rule in the grammar. Then we use the make keyword, and then we say what abstract syntax tree node we're actually going to use. Well, in this case, quote expert actually made one for us, so we just use whatever it made. That's kind of a very simple and boring case, so let's see a different one. Here is the one for the argument list. Well, for an argument list, all we'll do is we'll make a new abstract syntax tree node, an operation one. We'll go and build up this node out of the AST for each of the terms. So if you think about what we're doing here, we've been to our argument list, we've passed all of the arguments, and now after doing that, each of those has had a chance to make itself a little piece of abstract syntax tree. So what we're doing now on the way back up is we're sort of building up the abstract syntax tree for the whole argument list. Finally, we have our terms. So for value, again, it's just saying whatever the value node made. For the call, then you can see I get the one from the arg list. So that $arg list abstract syntax tree is actually what I made back on this slide. So it's a passed op node. Well, all I have to do is say that this is a call. You can see call there. We specify the name of the subroutine that we want to call, and then we say, just make this. And finally, we sort of finish up at the top. So all we're going to do here, we have a list of different terms, which are probably different function calls. And we'll just say, okay, I want to make a statements node, and I want to just take each of the terms, take the bit of tree I made for it, and just push it into this list. And then finally, we're done. We just say, here is the whole program in a tree format. Finally, we're just going to write our one WriteLine built-in. And all we're going to do is use the NQP built-in say function to implement it. And now we have a working compiler. We can actually run this. we can do the write line, hello, on type A, and it would actually work. And just to prove it to you, there we have it. So that's nice, but it's not really the whole story. We wanted to start adding some operators. We wanted to do string concatenation, and we want to do assignment. Now, one problem that you find when you write a compiler that's doing this kind of idea of breaking the program down into pieces is that getting the precedence levels and saying, oh, string concatenation is, say, tighter than assignment, for example, is actually quite hard to do with recursive descent. Thankfully, we build in what we call a expression parser, or an operator precedence parser, which actually makes this all really, really easy. So what we have to do here is just configure it by telling it what different precedence levels we have and giving them some kind of label. So here I'm saying, for now, I have the concatenation operator. It's left associative. That means that if we have A concatenated with B concatenated with C, then we want to do the A and B first and then join C on afterwards, rather than the other way around. And I'm just going to say that that's a concatenation operator. Then all I have to do, remember I talked about how we have the categories earlier? Well, all I want to do is add an infix operator. So this is just saying, oh, here's something for the category infix. And infix operators are just operators that go in between two other terms. So I'm just saying, well, I have this tilde, which is I'm going to be a concatenation operator. Now, that's just syntax. That's just parsing. So now we also need to give it a meaning. And all we're going to do is just call down to the virtual machine's concatenation operation. So we're assuming that the VM we're running on provides some kind of concatenation, and we're just going to use that. Finally, we're just going to do a little switch, because when we started out with this, we said our program was just some kind of term. But now what we'd really like our program to be is maybe an expression. We might have two different things concatenated together. So in a couple of places, we're just going to change term into expression. So that you can now, instead of just calling writeLine and writeLine saying, oh, it's a string, you can call it and you can concatenate two strings together. So after doing this, then we're actually able to do a concatenation. That's all we had to add. So at this point, we can take the string type A, we can concatenate the string 101, and we can writeLine them, and there we are. And if we actually were to do this, we can see that it's produced some virtual machine code, which actually calls the concatop, and this funny $P thing is just a register name. This is a temporary storage location in the low-level code. So we added our operators, but we only added one, and we need one more. The one more we need is the one to do the assignment. So what we'll do is we will add another precedence level. Now, this time, you'll note that we use right associative, because when you do A equals B equals C, you want to do the B equals C first, and then assign the result of that to the A equals. So that's sort of the opposite way around that we wanted. We've also, you'll note we said it was precedent Z there, and here we're saying this one is Y. It actually sorts these alphabetically. So you could have like yo-yo and zebra there if you wanted. But here we're just adding another infix, and that's going to do an assignment. And then we just have to write a little bit of an action method here. All we actually do in this case is we say, I'm going to make a node, and I want to be doing a bind of the second child to the first one. So this is all we have to do to actually get the binding operation to work. This is all handled for us beyond this point. We don't actually have to write the sort of low-level assignment-y bits. Now, that's kind of nice, but at the moment we haven't got anything we can assign to. We haven't got any variables. So we're going to have to add some. Now, when a compiler is compiling a program with variables in, it has to know what sort of variables they are. It has to know whether they live in this block, or maybe they're attributes of an object, maybe they're in the package. There's lots of places a variable could maybe live. The way it keeps track of this is by what we call a symbol table. So at the moment, we don't have one of those. The good news is that there's some built-in support for it, but it's built into a node that we call past block, and we haven't used it yet. So what we're going to have to do is, instead of having our program be wrapped in a past statements node, we're going to have to put it in a block one. And we're also going to have to track and have a sort of a knowledge of what block we're in. So to do that, inside our actions, we'll just declare my block. We'll add a method to create the past block node. So all we're going to do is just unshift this new past block onto this block array. How do we ever call that method? Well, in this top rule, we'll just call new block, and then we'll just say we have our bunch of expressions. And here, in the top one, all we're going to do is take the block we made and just push our program into it. So all we've actually done in this transition is just given us a way to store away what sort of symbols we have and change the thing that stores our top-level program statements into a block rather than a statements node. Don't worry too much about that, but here's the really useful bit now. Now I can add a rule for a variable declaration. I'll match the string var. We'll match an identifier. And then we'll just say, I want to make a past var node, which has this name. It is a declaration. And all we've done above is you see this dot symbol call? We've just said, take the current block and saying that it has a symbol in it that's called whatever the programmer typed in, and its scope is lexical. That just means it's sort of local to this function, but is maybe going to be sort of in an, if we have a nested function, for example, it would be locatable. Variable references are even easier. We just say if we have a variable, then it's just an identifier, and you'll see that all we do is name it here. This is why the symbol table matters, because when we're compiling this code and we see a variable name, we have to know where it's from. And in this is what we actually did on this previous slide here, is we've said, oh, if you see the name, it's a lexical. That's where you should look for it. Last of all, we just need to update our terms because we've got two new ones. So a term might be a variable declaration, or it might be a variable. We just have some little action methods, so there's nothing clever going on there. And that's it. At this point, we can now actually start using all of these language features together. So you can see that I've declared two different variables here, and then I'm doing a write line, and I'm concatenating the various variables together. So this will output I love type A. So we're actually doing pretty well, because at this point, we've implemented all of the non-object-oriented features in our language. And if we exclude comments and blank lines and so forth, we've actually only written 88 lines of code for a compiler that can sort of handle this little program. So that's not bad going. That's pretty small. So let's talk a little bit about object orientation and how we implement that. A while ago, I started a project which I call 6model. And previously, when we've given the compiler toolkit to people, we've said, okay, if you want to do object orientation, just work out how you want to do it. And sort of left that to developers. And for Rakudo, we sort of left it to ourselves as well. But we sort of realized after a while that it'd be what we actually wanted, if we're going to start making Rakudo more portable to different virtual machines, is to actually have a standard way to write all of this object-oriented stuff, We also had some quite special needs. We wanted to be able to do what we call metaprogramming, which I'll talk about in just a moment. We also wanted to handle something called gradual typing. Up until this point, the compiler toolkit has been extremely focused on purely dynamic languages. What we're actually doing now is trying to bring in a bunch of the static language elements as well, and trying to sort of build a tool chain so you can write compilers for languages that are either static or dynamic, or have features that do a bit of both, which is kind of what Perl 6 is. We also do what we call representation polymorphism. This is the idea that just because you declare a class with some attributes, you're not committing to a particular way of laying those out in memory. So representation polymorphism means that we can choose a memory layout for our object which is most suitable for the way that the attributes will be used. Maybe we only ever use, say, 2 or 3 out of 20 attributes in an object, and we don't want to have space for any that we don't use. Maybe we'd like to have as compact a representation as possible because we're going to have 10,000 of the objects in memory. So the idea of 6 model is maybe very similar to what you've seen if you've used anything like the Common Lisp object system or Moose in Perl 5. Basically, implementing classes or object-oriented features is done by just writing methods in some other object. To show you what I mean, imagine that we are compiling this class. We can see this class as generating sort of a sequence of events. So when we first see this, we can say, oh, we're declaring some kind of new type. When I see this method, I can say, oh, this is just an add method event. We're adding a method to this type. When I get to the end, I can say, oh, now I'm just going to compose this type. And you can imagine that there's a whole sequence of other events that we could have, like add parent class, or add a role, or add an attribute. So really, if we just want to implement a class, I mean, in this case, implement what classes actually mean, then all we have to do is write some code which handles the events. So here I'm writing a little bit of code which just has a method new type. So this is going to get called whenever we actually declare a new class. And it's going to create a new object to represent that class. So what it's actually doing is it's taking the name, it's creating a new what we call meta class, and the meta class is the thing which actually holds all of the class information itself. We're then saying how we want to store the objects in memory. Well, I've just said that I want to store all of any attributes just in a hash. We don't actually have any in this language, but if we did, then we could just store them that way. And then I'm just saying, make me a type object. Make me a type which is going to use this meta class to say what the object means, and that will use this particular memory layout. So that's our new type. And then we have compose, which is going to be called at the end of the class. Well, we don't want to do any work here. We don't actually have anything to do in this case, because we're doing a really sort of very straightforward class system. So now we've written that meta class, let's just go back to our grammar. And I want to just do a small refactor before I go any further, because so far we've just had terms. But what I'd really like to have now is statements. I'd like to differentiate statements from just any expression. So all I'm going to do is say that my program is a list of statements separated by semicolons, and that a statement is an expression. So at this point we haven't added anything, we've just refactored it. What we can do now, though, is we can start to add a new type of statement. We'll have a class. A class is just the word a, that's our keyword for a class. Then we have an identifier, which is the class name, like dog. And then we'll just match an opening curly brace and a closing one. And that's it. That's just sort of our empty class at the moment. I won't show you all of the action code because there's a bit of it, but all we really do is compile this to just making calls to the new type method and to the compose method. So here's the one for new type, and you can just see, you can see call method in there, and new type, and what we're calling it on is that tinylang class that we wrote earlier, and we're passing the parameter name. So you can maybe just start to sort of read out what that's doing. And don't worry if not, but essentially all you need to know is that we're generating code which will start making these calls on our meta class. So we're almost done with having classes. We just want to add a couple of built-ins. One of them is going to make new instances of objects, so that's our new. So these are just two new built-ins. And the second one is just going to be called type of, and it's just going to return the type of the object that we have. So at this point, we can actually write an empty class. We can say we have a beer. We can declare a variable Budweiser, which is a new instance of the class. And then we can just right-line the type of this variable, and it will actually tell us that the type of it is a beer, which is what we declared it was going to be. But of course, classes without methods aren't very useful, so let's just finish this up and add them. So if you think about what our meta object is, we've said it's the thing that knows everything about the class. It's the thing where we call methods on as we are passing the class and as we're constructing it. So all we're going to want to have is a method called addMethod. We're going to have an attribute, which is going to be called methods, which is going to be a hash. And whenever we add a method, we'll just put it into this hash. And whenever we want to find a method, so this is what gets called when we're doing dispatch, we'll just get it from the hash and return it. So that's pretty straightforward, and that's just putting things into a hash and taking them out. And that's all we actually have to do to write methods. We just need to pass them now. So all I'm going to do is say I'm going to have the word can. You remember that from our sample program. We have the name of the method. Because we want variables declared inside this method to only exist in there, we want them to be local, not global in scope, then we'll just call new block there to say this is a separate block. And then we'll just say, oh, our method is a list of statements separated by semicolons and surrounded by curly braces. The action methods then will just make calls off to add method on the meta object. And we're done. So if we just take a look at what low-level code the class a cow can moo that does writeline generates for building the class, you'll see that I've just picked out in yellow the sort of sequence of method call events that actually happen. So it makes the new type. You'll see that it's doing it on the tinylang class. It then does add method. It then does compose. So this is the code that we actually generate, having written our abstract syntax tree, which actually compiles that class. And at this point, we're done. Our example actually runs. So when we run this program, it assigns woof to the variable dog noise. It creates a new instance of the dog class. It calls the bark method, which prints out woof woof. We create a new instance, which is a puppy. We change the contents of the variable, and we just call the bark method again. So that's kind of nice. And one of the things to notice is that we actually have variables used inside the class which are visible from sort of outside of it. So that's pretty neat. And we've actually been able to combine all of these different features in our language that we've implemented sort of in a sort of arbitrary way. So that's pretty much all we've had to do to write our compiler. It's 181 lines of code to run this program, or pretty much any other program that we would write in this little language. We wrote a 40-line grammar to parse it. We only wrote 20 lines in the meta object to say what classes actually mean. And we wrote about 100 lines of actions if we want to make this work. And I'll actually post the code online afterwards if you want to get the full thing and sort of go through it all. The other thing that's really important about what we've done, though, is that we've actually developed this in a way that it's going to be really easy if we want to go and add a few more operators, or if we want to go and add new types of value or new types of term and so forth. So we've actually developed a compiler which is not only running this language, but is also pretty extensible to be able to sort of build extra features in as we go along. What's even nicer to realize is that the grammar and our actions are just classes. So if we want to make a version of this language which is the same but extended, then we can just do that by sort of subclassing the grammar. And that applies to Perl 6 too. If people want to take it and make a sort of domain-specific language or dialect within it, they just have to write a subclass of the official Perl 6 grammar, and then they have sort of a sort of extended version of the language in a completely clean way. So NQP is the language that we've been writing this in, and it's just written in the same way. It has a grammar class, an actions class, it has some meta objects, and it has a little bit of glue just to tie things together like we had. So if we go and look over in the NQP source tree, you'll just see that we have an NQP compiler class, we have a submain, we have a grammar class, and if we go and look down it, we can start to see it's got the tokens in that we'd expect. It's more complicated, but if let's find something that's not crazy. So you can see that we've got things like if statements in here, unless statements, and so forth. And this is actually just building upon all of the same stuff that we use to build our own language. So this not only is good for our little toy language, this is the same thing that we're building NQP itself in, and it's the same thing that we're building the Rakudo Perl 6 compiler with. And back here, we've just got all of our action methods, and you can see there's quite a bit of code in there. But really, it's all doing the same sort of stuff. It's all building up bits of abstract syntax tree, just like this. So that's some of what you can do today. Obviously, this goes pretty deep, and there's a lot to learn if you kind of really want to dig into making a big language. But the current stuff I'm working on is actually very much related to what we call gradual typing. So trying to not make this just a toolkit that's good for doing dynamic languages, but also getting sort of more static languages implementable as well. There's a bunch of stuff that we want to do with the documentation for this. One of the recent changes is that up until about a month ago, or maybe even less than that, you couldn't actually write the compiler completely in NQP. You had to write a little bit of low-level VM code to glue things together. Now you don't have to do that anymore, which is kind of nice. In the future, though, one of the really important things is that the compiler that we just wrote today wouldn't just run on the Parrot virtual machine. That compiler that we've written today would also be a compiler that's good to run on, for example, the .NET Common Language Runtime or the Java virtual machine. Now, I've actually started working on this, and I actually intended to just leave this slide here until yesterday. Jesse said to me something like, "Oh, it'd be cool if you showed off doing the CLR bit." So I figured I'd do a terrifying demo of the future. Now, this is kind of scary because I actually had to hack this up in the half hour before lunch. But essentially what we can do is we can take our compiler and we can cross-compile. We can actually run the compiler on Parrot, but we can generate code that will run on the .NET Common Language Runtime. So, let's have a look. Okay, so I'm actually just going to run the same program, the very same program, but I'm going to have to compile it first. Now, what we weren't doing so far is compiling it to a separate file and then running it. We're going to have to do that now. So to make that possible, I've actually had to take the meta objects and the built-ins and actually put them into a separate file. So I've done that. So that's in here. So that's actually just our meta class. And earlier on today, I actually compiled this bit of code into .NET CLR code. So you might have noticed that when I did this, there's actually, oh, you really shouldn't type binary files. Okay, but that's the .NET CLR output. So I didn't trust myself to get this right, so I wrote a little batch file. So let's see what it's going to do. All it's going to do is it's going to run, it's not just the tiny lang, I've called it the CLR one, and it's actually just configured a little bit differently to cross-compile, plus a couple of hacks that we won't need eventually. And it's actually going to output C# code at the moment. I haven't quite got it to emit the intermediate language yet, and it's a lot easier to debug just by emitting C#. And then it's going to feed that C# into the .NET C# compiler, and we should get a .NET executable out. So let's try it. I hope this works. Oh, a bunch of warnings, but it looks okay. So I fed in the dog.tl file, tinylang file. I got a C# file, and I fed that to the C# compiler. So what I should now have is an executable. There it is, 8 kilobytes of executable. And if I run this, there we go. It's actually just run this code on the .NET Common Language runtime with pretty much the same compiler we wrote to run it on the Parrot VM as well. So there's some work to do to make this seamless and easy, but it's kind of nice that it actually seems to already just work. So really what I want to do amongst all of this is just to make it easy to explore new language ideas, to make it easy to write domain-specific languages. I also really want it to get to a point where we develop languages and we can run them on Parrot or the JVM or the CLR and just have to write the compiler once. And of course, along the way of doing this, I'm really hoping that we can make a pretty awesome Perl 6 compiler as well. Thank you very much for listening, and I'm happy to take any questions. Nope. Oh, you have back here? Okay. Okay, okay. Okay, in that case, thank you very much.